In the macroscopic world we're familiar with, an object can't pass through a solid wall. But in the microscopic realm, governed by bizarre laws, a particle can pass directly through a barrier like a ghost. This is one of the most baffling phenomena in quantum mechanics, quantum tunneling. And the 2025 Nobel Prize in Physics honors three great scientists who, for the first time, successfully amplified and captured this quantum magic previously confined to the microscopic world, within a man-made circuit visible to the naked eye. These three scientists are British physicist John Clarke, French physicist Michel Devoret, and American physicist John Martinis. They were jointly awarded this honor for their experimental discovery of macroscopic quantum tunneling and energy quantization in electric circuits. This story begins in Cambridge in 1962, where a 22-year-old student named Josephson boldly predicted that pairs of superconducting electrons could tunnel through an insulating layer without any energy loss, opening the door to the study of macroscopic quantum phenomena. Over a decade later, physicist Anthony Leggett pushed the question further: could a macroscopic object, composed of billions of electrons, also tunnel through a wall collectively, just like a single particle? This question ignited a global scientific race. In the 1980s, at the University of California, Berkeley, a magic trio composed of leader John Clarke, theorist Michel Devoret, and practitioner John Martinis decided to take on this challenge. The team's leader, Professor John Clarke, a British physicist known as the godfather of superconducting electronics, provided the anchor for the experiment's success with his meticulous and rigorous style. Postdoctoral researcher Michel Devoret, from France, injected the team with imaginative theoretical insights. He excelled at asking profound what-if questions, serving as the bridge between deep theory and concrete experiments. And John Martinis, then a PhD student, was the master craftsman who turned all the wild ideas into reality, building the incredibly precise experimental setup with his unparalleled hands-on skills. To observe the faint quantum signals, they had to build an isolated quantum sanctuary. This was their weapon, a dilution refrigerator that cools down in stages, resembling a golden chandelier. This device utilizes the peculiar physical properties of helium isotopes to cool the chip to tens of millikelvins colder than outer space, and uses multiple magnetic sponges to shield it from all external electromagnetic interference. On this ultra-pure stage, their core weapon was a tiny circuit called a Josephson junction, for which physicists invented a brilliant analogy, the tilted washboard. In this model, a macroscopic particle, representing the collective behavior of billions of electrons, is trapped in a bowl-shaped potential well made of energy, corresponding to the circuit's zero-voltage state. At high temperatures, it's like we're shaking the bowl violently. The particle can gain enough thermal energy to jump over the rim and escape. This is the process of thermal activation in classical physics. But when they lowered the temperature to near absolute zero, almost stopping the shaking, a miracle happened. The particle still mysteriously appeared outside the bowl at a fixed rate. It didn't jump out, it passed through the wall like a ghost. This is the famous smoking gun graph from their 1985 paper. In the high-temperature region, the escape rate plummets as the temperature drops. But in the low-temperature region, the curve flattens into a plateau. This flat plateau irrefutably proved that even without the help of heat, the macroscopic giant particle could still pass through the wall. This is macroscopic quantum tunneling. They had truly created a Schrödinger's cat on a chip. This Nobel-worthy discovery proved that a Josephson junction could act as a macroscopic quantum system, which directly gave birth to the idea of using it as the basic unit of quantum computation, the qubit. But early qubits were like an extremely sensitive miniature swing. Any slight breeze of charge noise could make it wobble violently, causing the quantum state to vanish in just a few nanoseconds. Until 2007, when one of the laureates, Devoret, and his colleagues at Yale invented the revolutionary Transmon qubit, completely changing the game. Their brilliant design was equivalent to attaching a huge, heavy flywheel to that light swing, a large parallel capacitor, making the system incredibly insensitive to tiny charge fluctuations. This design physically suppressed the effects of charge noise exponentially, boosting the qubit's lifetime from nanoseconds to microseconds and even milliseconds, an extension of millions of times. It was the birth of the Transmon that truly made it possible to build more stable and powerful quantum computers, and it remains the core technology in quantum computers from companies like Google and IBM today. Fast forward to 2019. John Martinis, the PhD student from back then, had become the leader of the Google Quantum AI Lab, where he and his team dropped a bombshell that shook the world. They claimed that their 53-qubit processor, named Sycamore, completed a specific computational task in 200 seconds that would take the world's most powerful supercomputer 10,000 years to finish. This milestone, dubbed quantum supremacy, was intended to prove that on a specific problem, a quantum computer already possessed an overwhelming advantage over all classical computers. However, Google's claim immediately sparked a fierce rebuttal from its main rival, IBM, who argued that Google had severely underestimated the capabilities of classical supercomputers. IBM pointed out that by using a more optimized algorithm and leveraging the supercomputer's massive hard drive for auxiliary storage, the same task could be completed in just 2.5 days, not 10,000 years. This battle of the titans made the scientific community realize that the definition of supremacy is complex. Consequently, a milder-term quantum advantage came into widespread use, focusing more on solving problems with practical value. Today, quantum computers based on this Nobel-winning technology hold great promise for solving some of humanity's ultimate challenges, especially in the field of pharmaceuticals. German pharmaceutical giant Boehringer Ingelheim is collaborating with Google, focusing on molecular dynamics simulations, hoping to predict how drug molecules bind with proteins in the body with unprecedented accuracy. Meanwhile, another giant, Merck, is exploring the use of quantum computing to solve the common small dataset problem in drug discovery, hoping to bring breakthroughs to the development of drugs for rare diseases. Of course, these collaborations still face immense challenges, including the persistent noise issues in current quantum hardware and the need to develop more efficient quantum algorithms to truly unlock their potential. After achieving quantum advantage, John Martinis didn't stop. He founded a new company, Colab, dedicated to solving the most stubborn bottleneck facing the commercialization of quantum computing: scalable manufacturing. These challenges include how to ensure manufacturing consistency across millions of qubits, how to prevent signal crosstalk between them, and how to precisely control the frequency of each individual qubit. Colab's innovation lies in its business model of horizontal collaboration instead of working in isolation. They partner with established semiconductor giants like Applied Materials, aiming to transform quantum chip making from labcraft to industrial production. So, as you can see, from the 1985 experiment that proved the possibility, to today's quantum technology capable of solving real-world problems, there is a clear path of technological inheritance. The 2025 Nobel Prize in Physics isn't just for an experiment from 40 years ago. It's a tribute to an entirely new quantum era sparked by fundamental science. This is a story about breaking boundaries, from a theory 60 years ago to Berkeley's Schrödinger's cat circuit to the world-changing quantum technology of today. It broke the boundary between the micro and the macro, and even more, it shattered our imagination of possibility and the limits of computation. The charm of science lies in the constant exploration of the unknown, and this unending quantum dance continues to lead humanity in exploring the ultimate frontier of computation. What are your thoughts on the quantum world? Leave your ideas in the comments below. If you enjoyed this video, don't forget to like, subscribe, and share, and join us in watching this world being transformed by technology. See you next time!